Okay, welcome back to another week, and we are moving from electricity, the topic of last week, to waves, which is the last topic before our exam on Friday. So, yes. So let us get into this. We're going to start off with some definitional questions. The questions aren't right now, but go ahead and get connected to WooClap so you're ready when we get there. So I'll give you a few moments to get connected. And I will do the same. In case you're wondering, I use this computer to monitor the student responses. And 2 out of you have already connected. Nice. Okay, just remember that URL there. I'm going to move on, but you should still be able to get that done. Okay, so vibrations and waves. So a definitional thing. Now, the two of you, we have almost opposite classes that weren't here on Friday. We discussed having a quiz over vocabulary and definitions, and the students were very definitive. No, they do not give me permission to do that. So we won't be having a quiz on definitions. I do have definitions that I believe I already uploaded them to Moodle, and I will update it tonight after today's lecture to include chapters 8 and 10, because what is up there right now is just, I think, chapters 1 through 5. So a lot of vocabulary, and when I was doing the lecture preparation today, I added already these terms to that document. So vibration is a wiggle in time, is what our textbook says. So here is a very practical example of a vibration. I take a spring, I hang a mass in the spring, and then if I pull it down, it's vibrating or oscillating back and forth. Is it moving? Yes. But is it traveling to a new location? No, it's just going back and forth over the same path. So in time, it's wiggling is the definition our textbook uses. Now, there's important vocabulary words that go with this. And the next couple slides have more on these vocabulary words, but I'm going to talk about them now while I have this oscillating. So my first vocabulary word is simply going to be equilibrium position. The equilibrium position is the position where, well, you remember the term equilibrium. What does equilibrium mean?
Constant, like the same, right?
Okay. Equa means equal, and librium means forces. So it means that it's equal forces or the net force is 0. And so Newton's second law says if it's in equilibrium, if the net force is 0, then the motion must be constant, that is, there's no acceleration coming. Glad you are up and about. So,
no, I'm teaching you like 2. I'm going to come back.
The rest position is the equilibrium position. Now, second word, if I move this to a position away from here, then I've displaced it from equilibrium. So the displacement is the distance that I've removed it from the equilibrium position. So here it's displaced downward about 5 centimeters. If I let it go, now it's oscillating, right? We already talked about the term oscillation. And the maximum displacement, what is displacement, just to make sure we're remembering these things?
You're asking the wrong person.
I'm asking all 4 of you.
Exactly. Well, I am also the wrong person.
Yeah, you weren't here when we defined it.
Oh, did you say displacement?
Yeah.
Moving from something, the moving of something from...
I have no idea how to define these things, but I know what they mean.
It's the distance from the equilibrium position.
Right.
So the maximum displacement is the maximum displacement from equilibrium position. Now it's going up and down equally about the equilibrium position. and that maximum displacement we call the amplitude. So you just take the extreme minus the equilibrium position, that gives you the amplitude. So a whole bunch of words here we've had, and I'm not going to write them down here because they're going to be on upcoming slides as reminders. But we had the equilibrium position, the vibrations, the displacement, the amplitude. A couple more words, because yay, we need words. The frequency. You guys know something about frequency, like,
Do I?
yeah.
Oh.
What does frequency mean to you?
When I hear frequency, I think, wavelengths or like, what are those things, bats?
Bats?
I think repetitions.
Bats.
For
Repetition.
sound,
Solid one.
sound frequency.
Okay, sound frequency?
Like sound and repetition.
Yeah. So frequency is the number of times per second something repeats. So when I'm speaking, I am actually sending out a whole bunch of bursts of pressure. And those bursts of pressure are coming out somewhere around, let's say, 300 times per second. So the frequency is 300 per second. So frequency is how many times per second? Now
300.
let's put this in practical sense.
Did I not get it right?
What's the frequency? Well, I hadn't asked the question. What's the frequency of us attending lab?
300 per second.
Oh, once
Ooh.
per week.
Once a week.
Once per
Once a
week.
week.
Once per week. We do not have 300 labs per second. So, that's a practical understanding of what frequency is. Now, the opposite of frequency, and by opposite I mean inverse,
Inverse.
of frequency is the period. The period is the time between things. So what is the period for us having laboratory?
Laboratory?
Oh,
Do you need
it's 6 out of, right? Because you said inverse.
Well, the period is the time between, so it's the inverse. Yes, it is the inverse. We had lab with a frequency of once per week, right? So the period, the time between labs is
6 days.
actually 7.
7 days.
Yes, you're right, except for 6 to 7. Yes. So we have the period is 1 week, the time between labs. The frequency is once per week, which is just 1 divided by that. Or the period is 7 days, the frequency is once per 7 days. So if we look at this, the period, the time for it to oscillate up and down once, is about a second. And if the period is a second, what's the frequency?
1.
1, right, once per second. Now I'm gonna put a heavier mass on here, and I want you to tell me what happens to the period when I have the heavier mass.
It stays down long.
First of all, I can't have both of them on there, or now it still hits the ground. Okay, I can't use the heavier mass because it hits the ground. So we'll change it up and we'll go to a lighter mass.
Lighter mass.
Okay, so lighter mass, pull it down.
Lighter mass.
What happened to the period, the time between oscillations?
It
What
went
happened?
down.
Went down.
It went down. So changing the mass changed the frequency that it oscillated at. We call this, by the way, the natural frequency. So if the frequency went down, what happened? Oh, actually, the period went down. The time went down. So if it's less time, let's say it's doing half a second for every oscillation, then what's the frequency now?
Half.
If the period is half, the frequency is
2.
2, right? So it'd be,
You're a genius.
the frequency would be 2 cycles per second. Okay, all the words here, now we're going to review them again in kind of a sequence.
Let's review.
And
now.
actually, I need to do one more thing. All of this was on vibrations, also known as oscillations.
Yeah, you were using that word, and I was like, I don't know what that word means.
Yeah, oscillation is the same thing. It's going like this. That's what it means. Oscillating back and forth. Okay, a wave is a traveling vibration or a traveling oscillation. So an example of a wave would be something like, and I will have Vanessa hold this over here so everyone else can see. So you just hold one end of this and I'll hold the other.
Okay.
So if you hold it like this, and I move this up, it's displaced, its equilibrium position was here. I displace it from equilibrium and I let go, and you see that that displacement is now traveling down this blinking back.
How cool is that?
So that's a wave. Now this kind of wave here is called a transverse wave. Transverse because the displacement was perpendicular to the velocity. I could have also made what we call a longitudinal wave where my displacement is parallel. So that's two fundamental types of waves, but they're traveling oscillations. Okay, so now we're going to do a whole lot of review of these terms, along with two new terms on this slide. Well, one new term. We already talked about amplitude. What is on the vertical axis of this graph?
Wavelength.
Wavelength.
Oh, vertical.
Well, what is being measured in this direction here?
Amplitude.
It's not amplitude.
Oh, oscillation. The oscillation. What was the word?
Okay, I was gonna say.
That is a correct word, but it's not what's being measured there. Just tell me in plain words, not trying to use a vocab word, what's being measured on the vertical axis?
Distance.
How much
Wait.
it bounces per
Bounce.
second or whatever.
Okay. All right.
I feel really bad because I cannot focus at all. Like, it hurts.
I don't
I'm just
understand.
trying, okay?
And you know what? Unlike a television, whacking you upside your head is not going to make you better either.
Oh, yeah.
The vertical axis is measuring the position of that mass.
Position of the mass.
I knew it was.
And so if we think about this,
Position
the mass
of the mass.
has an equilibrium position that's right here. So this is its equilibrium position, right?
Yes.
Couldn't fit it all in one word. Equilibrium position is that green dashed line.
Green dash line. Okay.
Now, what do we call it if I move it away from the equilibrium position?
So what?
Displacement.
Displacement. So that's what we actually wanted the word for this axis. Displacement, how much it's moved away from equilibrium. In plain words, you would say it was the position of the bog. But the position is measured relative to its equilibrium position, and that's what makes it displacement. Okay, you had a question, Annabelle?
I take back my question.
You take it back, okay. So you have displacement on the vertical axis, and the horizontal axis is
Are we gonna have to label this on the test?
you're not going to have this specific graph, so I suppose not.
We're gonna have to
But
label a graph.
You do need to be able to read the graph and understand what the graph is doing, yes.
So, but no.
So I put position here. The reason I know it's position, even though it doesn't really make sense with the picture, is because it has the word wavelength. So here's what has to be going on for this picture to make sense. This picture is, I should just use my own instead of this one because it's a poor example.
That's okay.
This picture is illustrating this situation. Okay, not doing well. This is supposed to be oscillating up and down, and this is moving side to side.
Moving side.
That's what the picture is supposed to be illustrating because it is a moving oscillation.
Oscillation.
But of course, you would rarely have your spring moving along. Wavelength here is the term for the distance between a peak and another peak, or between 0 and 0, or a trough and another trough, or just some random position when it reaches that same random position.
Random position.
So the wavelength is technically the distance it travels in the time it repeats. What do we call the time for it to repeat?
Repetition.
Frequency.
Repeated frequency.
Period.
The period. The period is the
Period.
time for it to repeat.
Oh.
And so the wavelength is the distance it travels in a period. Now, we have already learned about motion, and we learned that speed is change in position over change in time, right? If speed is change in position over change in time,
Right.
Then what's-
Change over time.
then what's the equation for change in position?
Change.
Changing
Wait,
position divided
The
by time.
opposite.
That's what speed is. So what is change in position? If I just solve this equation for delta x,
It's T, delta T.
Yeah, times delta.
okay,
Times delta T.
it's the speed times delta t.
Yes.
That's what I said.
And so we said that the wavelength is the distance it travels in one period. So now we have some crazy symbols.
Crazy. Oh, God.
T
V is speed, right?
is the symbol we use for period. T stands for time. And yes, V is speed. That's correct.
Flip.
And wavelength, you'll never guess what this is unless you already knew. It's a Greek lowercase l.
Oh.
It's pronounced lambda.
Oh. Yeah.
It's the Greek lowercase l.
The X?
No, that's what our x is going to be. The wavelength is lambda.
Yeah.
And so delta x for one cycle, the distance for one cycle is wavelength, equals the speed multiplied by the time for one cycle, the period. And so we have the relationship that wavelength is equal to speed times period. But remember, we said frequency and period had a simple relationship.
Right.
Frequency, we use the symbol F for frequency. That one makes sense, thankfully. Lowercase f, so we don't get it confused with forces, is 1 over period. So I can also write this as speed over frequency is wavelength. So a whole bunch of equations here.
Yeah.
That's 1 over time.
Frequency is 1 over period. The T does stand for time, but we use that's specific to period when we use the capital T.
Okay.
So, reviewing terms again, what is the word for how far this is removed? Well, the start,
Displacement.
Yeah.
that was the
I am
answer.
a genius.
What do we call this position? Equilibrium
Equilibrium.
position. Displacement. What do we call the maximum displacement?
Natural frequency. No, I don't know.
It's on that picture.
Wave amplitude.
Amplitude. The maximum displacement is the amplitude.
The
What-
max displacement.
Maximum displacement, yes. What do we call the time it takes to do one cycle?
Period.
Period. What do we call the number of cycles per second?
Lots of periods.
The frequency.
Frequency.
And there's one more thing before we get to the clicker question, I have to introduce, and that's units. But I think it's on another slide coming up. Don't even need to talk about that because we talked. Nope, it's not. But it's not on this question either. So let's go ahead and answer.
Bless you. Is that yawn? Bless you.
There you go.
Yeah, it came out. Yay. Okay, so WooClap, remember it's www.wooclap.
Are we doing blue cloud right now?
Yes.
Let me some blue cloud.
And these are C's.
The distance between adjacent points in the triangle. I don't understand these terms, like these words. Can you dumb that down for me? Me.
The don't worry about the word transverse. We've talked about it, but that's
Can you just
not
like,
important for
rephrase
us.
that without the big words?
I don't know how to do that.
Guessing.
Boom.
Okay.
I just don't understand.
What's
I'm really trying to figure this out.
Adjacent means next to each other.
What is the difference between the tops of the peaks called? Right?
In other words, the distance, here's one peak, here's an adjacent peak.
What's the distance? What's the word for that?
Yep.
Can you go back to the thing before that?
I did it.
Wait, can you go back to the meeting before that?
Well, this is checking if you remember. If I go back, you just read it.
I don't know. Oh, no, I don't get one.
I literally, it could be the number. Oh, voting is closed.
Yeah, open it back up. Go ahead and answer.
I'm guessing, but I'm probably wrong.
Okay. We have 3 out of 4 answers, and I'm not confident we're going to get any more. So we had 2 people that said frequency, 1 that said period.
Oh, my answer didn't go through, I guess, but I said C.
Okay, and 1 that said wavelength.
Yeah, it was closed when you were doing it, and I was like, how did you vote?
Okay, so the distance here, so now going back, right, the reason we ask these is to make sure that you're paying attention, that you're learning the things. If we go back to this picture, what was that distance called?
Yeah, wavelength.
Wavelength.
Hey, everything.
Wavelength is the distance for the wave to repeat. And so, as I said here, it could be from peak to peak. It could be from trough to trough. Trough is the low part, and it's not important to know that one.
Okay.
Could be from equilibrium to equilibrium, but it has to repeat. Now, you might have, when you looked at this picture, said, wait a minute, here is also equilibrium. So why is that not the wavelength?
Right. Wait.
It's not repeating because in one case it was moving up, in the other case it's moving down. So that's not repeating yet, even though it's at the same location. So when we say peak to peak or trough to trough, it's clearer because it's always repeating. It's always at, it's an amplitude at a trough or a peak. Okay, so the wavelength is the distance that it travels before it repeats. It's the distance it travels in one period, but period is time. Period is the time to repeat. That is a true statement. Wavelength is the distance to repeat. What is amplitude? Go ahead, Vanessa.
That's a question that doesn't even have to do with this class. I'm sorry.
Oh, okay.
What's it for me?
What?
Oh man, that's a deep question.
To me, that's a theological question, and I believe the answer is yes.
That's why I was like,
But-
no, that's not for class.
Amplitude. What is the amplitude?
Amplitude. Go back. I
Oh,
need a
it's
visual.
the maximum displacement.
The maximum displacement. So the amplitude is this distance here or this distance here. Because it doesn't matter if you're going up or down, the displacement is symmetrical about, and what do we call that green line?
Equilibrium.
The equilibrium position, right.
Genius.
Okay, so we've defined all the words here except for frequency. What is frequency?
It's how many times something occurs a second.
Right. How many times something occurs per second?
Right.
A lot of repetition on these vocabulary words. Hopefully we get them nailed away.
Well, let's hope.
Okay, so unit for frequency, hertz, abbreviated HZ.
The unit for frequency is hertz.
Yes.
You stole mine.
Sorry.
And a hertz is 1 per second.
Are we allowed to ask that?
Ask what?
1 hertz equals what?
It goes 1 per second. 1 cycle per second, 1 something per second. So when we talk about something like a sound wave, instead of saying there are 300 bursts per second, we just say it's 300 hertz. 300 of the things per second. Or coming out of the wall. Does anybody know what the frequency is of the electrical signal coming out of this wall?
No.
Why would we know that? I don't know.
I'm-
53.
It's-
700. 200.
It's actually really important if you travel.
Oh, well.
Because some countries use our standard of 60 hertz. Some countries use 50 hertz.
Or 60
And-
hertz.
Depending on what you're using, you could destroy it by plugging it into the wrong frequency. Okay, what was your question, Vanessa?
Okay, so
1 hertz equals what? I thought it was supposed to be 1 over t.
Okay, the relationship between the period and the frequency. Period is 1 over frequency, or frequency is 1 over period. So that's correct. But this unit of hertz is a unit of frequency, so it has to have units of something per time. And so it's 1 over second is the unit. Excuse me?
I'm going to keep pushing through.
Okay.
You know what? You're doing great. Keep going. I'm learning.
Yes.
All right. Second question then.
Second question.
If the frequency of a particular wave is 20 hertz, its period is Wu clap, yes.
I'm trying to focus.
I'm trying. Y'all just
20.
okay. Wait, no, we said that for 1 hertz, it's 1/2 of a second. 1/1/2.
No, that was 1 over a second is a hertz.
That
What
is
the hell?
I'm
not.
gonna do this one. Gabby's right, but I'm gonna do it.
Oh, girl, you are me.
I'm supposed to be teaching today and I can't even focus.
She's literally like,
It's okay.
me every day of my life.
It's okay. I'm gonna cry.
Okay.
That was a whole mood. A whole mood.
Okay, everyone's answered.
Yay.
We had 2 that said a 20th of a second, 1 that said 20 seconds, and 1 that said none of the above. Okay, for the first time in a while, the plurality is correct.
Was it? What?
The plurality.
I don't
Well,
know.
that is
Pl-
You and
pl-
your words.
Plurality.
Your
Okay,
words.
when you have an election,
Huh.
you have a simple majority, which is more than 50%,
Right.
or a plurality, which is the highest vote getter but not a majority.
Totally.
And so 2 was the highest vote getter, but it wasn't a majority. It wasn't over 50%.
Right.
Hence, it's a plurality.
Oh God.
In general elections, you can't win with a plurality.
You cannot.
You have to have a majority.
This is strange.
Okay, so since the definition of period is 1 divided by frequency, then that would be 1 divided by 20 hertz if I just plug that frequency in. But since hertz is 1 over seconds, that's 1 over 20, 1 over seconds. Divide by fraction. Do you guys learn how you deal with dividing by fraction?
Yeah, at some point.
Yeah, you invert and
The
multiply.
reciprocal.
You invert and multiply.
It's called the reciprocal.
The reciprocal is the invert, yes. So frequency is the reciprocal of period. So that's 1 over 20 times seconds over 1, which is, of course, 1/20th of a second.
I did not follow that. Okay. Dang it! I think I'm gonna say that I put that one. I'm claiming whoever's answer that was. I got
Okay.
it right.
All right, so sound waves.
Sound waves.
Actually, not sound waves yet. Ocean waves first. We have a bird here, and in this picture,
Can you name it?
yes, it's a dodo bird.
No,
His name is Fred.
give the bird a name.
Okay,
His name is Fred.
Fred.
Okay.
So Fred is sitting here on the dock of the bay, watching the waves roll in.
Same, dude. Same.
So, look at this picture. What are the 2 things that you can read directly from this picture?
Wavelength.
Wavelength. What is the wavelength symbol?
1. M.
The wavelength symbol?
M.
Lambda.
The upside down Y.
So lambda is 1 meter. What's the other thing? And that's the wavelength. I'll write that here. What's the other thing you can
Amplitude.
directly read? You cannot read
Well,
the
you
amplitude.
can't actually. Whatever V, volume. V is vector, volume. Oh, speed.
Yes,
Oh.
speed.
Okay, but then there are little sticks on the side. So,
The reason I write my V's that way is so that they're distinct from the Greek letter nu, which we actually usually use for frequency. We're using F for frequency to make life easy. What is
I love that.
what is the frequency in this case?
The frequency.
You can see the
is
confusion I would have
1
with V and nu if I
over
did.
1. So it's 1.
It's what? Oh, it's 1 over what?
It's 1 over, literally the only numbers available right now are 1. So I'm assuming it's 1.
You're assuming incorrectly.
Is it 2?
Frequency is 1 over the period, and we don't have the period. But we have the wavelength and the speed. How can we find the frequency from wavelength and speed?
Like how fast
Sure.
it is to move.
I wouldn't have known that.
That's how fast the wave is traveling in. Yes, what we're looking for. What we learned before was that the speed, the wave speed, is equal to wavelength multiplied by frequency. So what's the frequency going to be?
Oh, pause. So I'm trying to think here. It's 1. I don't know. Wow, that's a lot of math. Just kidding. Keep going.
If we solve for frequency, we have to divide both sides by lambda. And frequency is V over lambda, speed over wavelength. In this case, since they were all ones, it's still going to come out to be 1 meter per second divided by 1 meter gives me 1 in units of 1 over seconds, which then is 1 hertz. And finally, now that we do know the frequency, we can plug it in there and find the period. And sure enough, since everything is ones in this problem, we end up with the period is equal to 1 divided by 1 hertz equals 1 second. I know it would have been better if we'd had numbers other than 1 here, so that we could actually, practice doing some math instead of just saying, well, the number is 1 no matter how you arrange them. But by looking at this picture, even though we only had the speed and the wavelength indicated, and they weren't indicated by name, although I know in the example it had the words there to say, we can determine the frequency and the period from that data. We've already done the example of the transverse versus longitudinal waves. What was the key to a wave being a transverse wave? When the displacement is perpendicular to the motion. So the way I remember this, and we'll move on at devices, is a capital T has 2 lines that are perpendicular. And the transverse wave is the wave that has the speed perpendicular to the displacement. The longitudinal wave, don't think of what I just used because you can use it for longitudinal as well, is where the displacement is in the same direction as the velocity, parallel, as you said. Now let's think of examples of these. Can you think of any kind of wave that is a transverse wave? How?
The L's are parallel.
The L's are parallel. I love that.
The L's in parallel are parallel? Okay. What can you give me examples of these 2 types of waves? Name an example and make sure you identify which type it is. And if you don't know any, just say I don't know
I
any.
don't know any.
Oh, that one is that one that you did. The bottom one is. Oh, we have to give an example of it.
Yeah, I know that's not exactly.
Would the bottom one transverse be like waves like in the ocean?
Okay, this is, if you look at this picture, that it seems that that's yes. It turns out that ocean waves are a combination. Ocean waves, you actually have the water is doing like an elliptical pattern. So it's going up and down and side to side. And so it's a combination of the 2.
Sound waves?
Okay, sound waves are one of these 2.
Is the bottom one?
Nope. The top one is an example of a sound wave.
I tried that.
And that's perfect. There's nothing wrong with that. in a sound wave, my example, I'm sending out bursts of sound. If air molecules come out of my mouth, what direction are they going to be moving?
That way.
They're going to be coming out, right?
Right.
So the air molecules are going like this, and the sound wave is going to you in that same direction. So that's why they're longitudinal. Now, if I have a guitar, how do you play a guitar?
Down.
You pluck the string, and what direction does the wave move on the string?
Will it come back out?
It goes up and down the string. But you didn't pluck it in the direction parallel to the string, you plucked it perpendicular. So a wave on a string, so I'm just going to put guitar string here, is an example of a transverse wave. So we have both of them. Now, earthquakes. Have you ever been in an earthquake?
No.
Yeah.
Okay, we got some yes, we got some no. You said yes. Where were you in an earthquake? What state?
Okay, I was in Kansas.
In Kansas.
Kansas.
It's a rarity for Kansas to have earthquakes, but you know, the largest earthquake that we've had in the U.S. was in New Madrid, which actually I can't tell you what state it is. I think it's Missouri, but it's in this vicinity. So when you were in the earthquake, what did it feel like?
Shaky.
Shaking. What direction?
That's right.
Okay, side to side?
Yeah.
Now the answer depends on the earthquake you're in and where you are with respect to the focus of the earthquake. The focus is the place where you actually have earth slip against earth. You probably are familiar with a different term, and that's epicenter. Epicenter is placed on the surface of the earth directly above the focus. Focus can also be called the hypocenter. So if you're directly above, it still depends on the kind of earthquake. So motions for earthquakes can be a transverse wave, or it can be a longitudinal wave, or it can be a combination of the two. Depends on where you are. So you might go up and down, you might go side to side, or you might roll. And so those are the surface waves, the kinds of earthquake waves we have on the surface. And we call them Rayleigh waves and love waves. So you could be a Rayleigh wave, a love wave, or a longitudinal or a transverse. Any one of those. Going through the earth, which will be important when we get to earth science, it's only going to be either a longitudinal wave or a transverse wave through the bulk of the earth. So we'll look at these different types of waves coming up in later sections of physical science. So now looking specifically at sound waves. A sound wave, which type of wave did we say it was? It says right here.
Wait, what?
Which type? Transverse or longitudinal?
Longitudinal.
It's a longitudinal wave. So here there is a tuning fork. The tuning fork, you bang it and these two forks go back and forth. And so it's causing pressure waves. Pressure, force per unit area, is traveling through the air. And your ears hear, because first we have the outer ear. The outer ear condenses the waves together.
Right.
So that the energy of the wave, a traveling wave, carries energy. And if you condense it, you take that energy and put it in a smaller region, and we say that raises the intensity, the energy per unit area. So the outer ear is important for amplifying sound. Hence, back in the day, people who were hard of hearing would carry an ear trumpet. You ever seen pictures of an ear trumpet?
Yes.
Yeah. It's like a big bell on an instrument you put to your ear, and it collects the energy, puts in a smaller area, so it's louder. Then we have that tympanic membrane. The tympanic membrane, a membrane of flesh that when there's pressure on one side, it pushes in. But when there's lower pressure than atmospheric pressure, the atmospheric pressure on the inside pushes out. And so the tympanic membrane goes up and down just like a drum head on a drum. And then underneath that, you have a lever. An example of a simple machine. The stirrup and anvil is a lever with a short arm that will move with the tympanic membrane, and a long arm to then amplify the sound further, where it goes into our cochlea, and we have little hairs that vibrate with the sound to detect sounds. It's very complex. We were created in a pretty complicated manner to optimize so we can hear better. Sound travels at a pretty high speed, 340 meters per second. How much is 340 meters? Well, that's about 1/3 of a kilometer, right? A kilometer being 1,000 meters. And a kilometer is, well, a mile, a kilometer is about 2/3 of a mile. So 1/3 of 2/3 would be about 2/9 of a mile, or let's just say 20% of a mile. That's how far sound travels in just 1 second. Now that's fast, but it's not that fast. When I was young, went to my grandma's house, and my older cousin Rob was shooting my grandma's .22. It was a fun place. From a distance, I saw Rob fire the gun, and then a little bit later, I heard the gun report, like, half second later. And I thought it was hilarious. I did say Rob the first time, right? He's the younger brother.
And you said Rob.
I said Rob, yeah. So I thought Rob is afraid to shoot the gun, so he's flinching just before he pulls the trigger every time. And as I walked over there, the time between the two got smaller and smaller. So when I was next to him, I heard the report the same time I saw him move. Now we saw here that sound travels about 340 meters per second. When I was next to him, I saw him move and I heard the sound at the same time. Why were they not at the same time when I was farther away from him?
Because the waves weren't at your ears yet.
Okay, it takes time for the sound waves to get to me out there. Now light is also a wave. So it takes time for the light wave to get to me, but light travels at 300 million meters per second. So light travels many miles every second, 300 million meters every second. And so the time delay for the light is really not measurable, to you and me. Whereas the time delay for the sound was measurable. There are words here that I don't emphasize: rarefactions and compressions. I'll put them in the vocab, but compressions are places where you have high pressure. Rarefactions, places where you have low pressure. Where do you get the name rare from? Well, if it's rarefied, that means that the molecules are rare. There's not as many molecules in a given volume. The density is lower. So that's what the rarefactions is actually meaning. Places where you have a lower particle density. Compressions, you have the higher particle density. So in the picture, you could draw a box. And if I draw the same size box, there are a lot more molecules in the compression region in that box than there are in the rarefactions region. And so if you look at this, I'm just going to start here. How far do I have to go to get to one wavelength? So I will change to red color, and I'll draw along, and you tell me when to stop when I'm one wavelength away from this.
Stop.
Perfect. Because that's the distance for it to repeat. So the wavelength is, distance to repeat. It was pretty easy to see where it repeats, and as long as you remember what the wavelength meant, which you did, then it's not hard. Good old sound waves. We have lots of sound waves. We have speakers. These days, you usually have headphones, not so often, actual sound speaker anymore. We have microphones. What are the speaker and microphone fundamentally doing? Why do we have, for instance, microphones when you're up in church, they give you a microphone, they tell you, speak into the microphone. Well, what is the microphone doing?
Amplifying your voice.
Yes,
In and of itself, it's not amplifying.
vibrations and
Making your voice louder.
what it's actually doing is not making your voice louder without the amplifying. It is converting your voice signal into an electronic signal. It's taking it from being a longitudinal wave and making it to an electrical signal. And then that electrical signal is amplified because that is, we want to be able to, number one, record, number two, amplify, and rebroadcast. So then what is the speaker doing? We send the electrical signal to the speaker, and what's it doing?
Mimicking the message it receives.
Okay, mimicking the message it receives. It's taking the electrical signal it receives and converting it into a longitudinal wave. So if you were to take these things apart, the microphone has something in there that is going to, let's just make a simple type of microphone. You put a spring here, and when a sound wave hits it, the sound wave, remember, it's carrying pressure. And so when you have high pressure, the high pressure is going to cause that to move in, and when you have low pressure, the spring is going to push it back out. And so that little membrane in the microphone is moving in and out with the pressure of your sound wave. And then that motion is what is converted to electrical signal. The speaker is exactly the opposite. The speaker has a big piece of paper, and it has an actuator. We're not going to go into the method it works, but the speaker itself will move back and forth based on the electrical signal it gets. And when the speaker pushes forward, it creates a high pressure. When it moves back, it creates a low pressure in front of it. And so it's creating high and low pressures by moving that paper. And so that's how we use our audio systems. So if you have, you've got your phone there, and if you listen to something on the phone, like you have a phone conversation, or you listen to an MPEG or something, you have something that's pushing air in and out. So if your phone is playing sound, you can move your hand around and you can find where the speaker is, and you will feel the air pressure that's being caused by that speaker. Which, I know, kind of actually annoys me, but it's a reality. You can't make sound without having those pressures, because sound is a pressure wave. Okay. The speed of sound varies with temperature. For about every 1 degree increase, and that's 1 degree Celsius, increase in temperature, the speed of sound increases by about 0.6 meters per second. So if it gets colder, the speed of sound drops. Hotter, the speed of sound is faster. But the speed of sound in something like steel is 15 times faster than in air. And, well, let's think about this. You guys are way too young to have watched The Lone Ranger when you were a kid.
You're assuming.
I am assuming.
I watched
Maybe
it with my
you are
dad.
big, yeah. Huh?
Yes.
How about this? Have you seen High Noon?
Girl, yeah.
Who started it?
I don't remember.
Yeah, so, I've seen all the spaghetti westerns, but I don't think it's a spaghetti western. I have seen one of the westerns. Okay, with railroad
Gary
tracks,
Cooper stars in it.
right? Not right.
Gary.
You don't have to dress up there, but no, it's not.
I get it.
Anyway.
Wow.
in those old movies, to hear if there was a train coming, they put their ear next to that rail. Have you ever seen anything where they've done that?
No.
No. Okay. Well, we have two people who said yes. And the reason they do that is twofold. Number one, when I have a sound wave in the air, like that train's coming down the track, that train is, of course, making sound. You can hear a train from a good distance, right? But that sound is going out in all directions. And so the energy is spreading out over a bigger area, making the pressure smaller as it goes away. So the pressure getting smaller makes it not as loud. So the sound becomes pretty faint when you're far away. But in that rail, the wave just is going along this rail and staying pretty constant. And so the rail will maintain that pressure a lot farther. It will have a louder sound much farther away. And second, it travels about 15 times faster in the metal than it does in the air. And so they can hear that train from afar by listening to the rail when they can't hear it in the air. And likewise, Tonto would put his head down to the ground to listen for the horse hooves, because the sound also travels faster and more efficiently through the ground than through the air. The homework is due Wednesday. I think today's Monday, right?
Oh my goodness,
But-
Dr. Webb, you can't do that to me.
We're
Well-
gonna be okay, I promise.
Yeah, I put it up last Wednesday morning, so you would have a full
I know.
week. And I told you in class last Wednesday.
No, it's okay.
Sorry, lesson plans have gotten me to the point where I don't do homework or I don't have time to, because if I don't pass my lesson plans, it's 30% of my grade.
Whose class is up here?
Yes, Pamela's.
I know, I
Well,
figured
you can come to me for help.
Tragedy.
She's a great woman, but
Oh, no, yeah.
she don't understand when people be crying that they should not be crying.
Is the lesson plans the ones that they showed us in like, it's like the whole school year and everything? It's like, what is, why?
You have to be, here, I'll show you why. Look, let's see. So you have all your standards, but then you have to go over each individual standard and why you have that standard and how you're gonna teach that student and why that student needs to be taught that way and is it formative or summative and
Thank you.
We love that. It's gonna be okay, friends.
Are you at CPA, Josie?
me, I'm a Georgetown. I can remember Bible stuff, I'm not good at it, I haven't read it in so long.
I would not be able to do it in good consciousness.
I have to fake it till you make it, y'all, 'cause it's not always gonna be so fun to teach.
Hello, David.
Greetings.
Salutations from the church in Lincoln. Greetings.
Somebody left a pencil behind. I don't care for it, so I'll just throw it right there.
It actually was on the floor last week. Somebody picked it up off the floor. Round, round, you round, I get around, yeah. I get around, I get around. Dun, dun, dun. Ba-da-ba-ba.
We have an exam tomorrow.
Yeah, we do. Dun, dun, dun. I get around, round, get around, yeah.
Wait, so what are we going over tomorrow?
Ampere's law.
Oh, yes, I'll pair. I remember we briefly discussed him last.
And of course, everyone in the United States is going to say ampere, and since I'm not French, I'm sure I'm saying ampere wrong anyway.
Good morning.
Good morning. Yes, that is a much better door.
It is. It is. I never remember that door.
No.
Hello.
Good morning. That is the look. The glasses flipped up.
It's my like low-key goth Disney vibe today.
I have a proposal.
Oh yeah?
Let's move the test another week.
No.
One more.
There's no way. There's no way we can have tests in back-to-back weeks.
Same year, okay, 2 more weeks, then we'll have them on the same day.
They have the same.
Two
Oh,
tests same day.
that's
Yeah.
genius. Good plan.
Yeah.
I'm sure that would lead to success.
Somebody will.
I don't like the group test idea. Corinne thinks it's a good idea, but I'm like, but are we doing any differentiation? Because the whole point of the test is to differentiate the students, and if you combine them, how are you differentiating?
I know that from her class, with the way that tests are, it gives me a better understanding of like where my weak points are to do it with another student and where their weak points are too. So like my lab buddy and we haven't done it yet, but we this week are gonna get together before the quiz, like study together. Because we know where our weak points are usually gonna be. Which I think if we have like a really strong student pair who's like the strongest student in the class are gonna be the weakest student in the class, like it wouldn't be very reflective at all. But for me, it's
So I'm going to go through the grades and say, oh, these are the top 2 students. I'm going to pair them. These are the bottom 2 students.
it's good
No,
to learn exercise for me.
Okay.
I learn more from that style than just like getting the test for myself.
I think most teachers like the concept of having no exams and having no grades. UCSC did that. I don't know if they still do, but the problem is you get to when I was in grad school, one of my professor's daughter went to UCSC, and they had an option of getting grades or getting comments. And so she went with comments. So she had no grades in any class, just pass fail, until it comes to her senior year. And they're like, well, we have to assign you some kind of GPA. So we're going to give you a test, and based on your score on this test, you will have a college GPA. That was very harsh. But the idea is the teacher gets to know each student, gets to know their strengths and weaknesses, and evaluates them individually. And so you don't have to have a test then to differentiate because you know each student's strengths and weaknesses. And the problem is it's fuzzy. Like, well, this student knows stuff well. How do I rank them on a scale?
Yeah. I think my favorite, just since like class hasn't started yet, unless you're usually excited. I think my favorite like learning process I found so far is just like continuous testing. Like you start with a test, and then you're like, oh okay, like you learn these things, so take another test. Oh, okay, you need to learn these things, and you just like keep doing that until you get 100. But you start out with like a grade of like 40 or something. So it's not like grades for the sake of grades.
Mhm.
It's like testing to see what you know continuously and see what like you need to know.
Mm.
So for me, that's been the most effective learning style so far. But it's not really set up well for education on a large scale.
Well, it works well, I think, for online learning. It also works well for independent learning because you have a pre-test, you have a learning module, you have a post-test.
Yeah.
If you don't score high enough in the post-test, you go through more
Not even
remediation.
Like scrap the whole regular learning process. Like take a test. What do I need to learn? Take a test. What do I need to learn? Take a test. What do I need to learn? And just like brush up as you go instead of like, do I know any of these things? Learn it. Have to try those things. You know. So like you just learn continuously until you know all of the things on the post test.
You're all here but one.
But that'd be like really horrific if it were implemented like in an education system.
Well,
But it works great if it's like one teacher and like 5 students or something.
when you turn around, I didn't hear you.
Oh, it works really great if it's like a very small number of students to teacher ratio. I've seen it work well in homeschool systems, but that's about it.
Yeah. There's also a time element when you have a whole class.
Yeah.
Because this person's done, in 2 weeks, and this person, like, well, I don't know. We had these SRAs when I was in grade school, and I was good at these. And so I finished the entire bin. I just did them all while other people had only gone like this far. And, then the teacher's like, well, what do we do with Richard? Let's get next year's and have him do next year's.
I think for me, it takes away like testing anxiety because tests are never like exactly reflective of what you learn in class.
Yeah.
Like in class, you're always learning like extra stuff or slightly different things, and then tests is always like a little different than what you expect. So for me, it's like.
And there's also like,
more
in physics,
clear on what I need to learn. Yeah.
in physics,
There's
the
also
questions
physics,
are
it's
not
just-
the questions you, oh, good. I'm still recording from the